Today I want to talk about domain ball pinning in bismuth ferrite multiferroic using global optimization methods. Let's first of all start from what is the bismuth ferrite multiferroic. It's bismuth ferrite have a perovskite-like structure. And as a multiferroic, it possesses both ferroelectric and antiferromagnetic order. I want to mention that the bismuth ferrite is the first type multiferroic. It means that ferroelectric order is stronger than magnetic order, and the ferroelectric order is leading for this material. But antiferromagnetic ordering temperature is quite high, 650 Kelvin about, and it allows to study properties of this material at room temperature. And also there's a number of suggestions how to use this material in practical applications. I want to say that bismuth ferrite shows a few order parameters. Ferroelectric order parameters is electric polarization, which you can see on the left side of the slide at the picture, the vector P. And second order parameter is anti-distortion vector, which is lambda. Sorry, I mean omega. Anti-distortion vector is a difference of rotation vectors omega 1 and omega 2, and it describes oxygen octahedral rotation in neighboring pseudocubic perovskite-like cells. And they are also in bismuth ferrite 2 magnetic sublattices, which is denoted as M1 and M2 ordering parameters to magnetizations. But we will describe these magnetic properties using the Neal vector, which is the difference of two magnetizations of sublattices. Let me first say about possible equilibrium magnetic states. There are a number of equilibrium magnetic states at zero magnetic field and at room temperature. The main the equilibrium magnetic states is described by a spin cycloid structure, which is shown as a subfigure B. A spin cycloid or spin spiral is a spatial rotation of magnetization in some crystallographic direction. We will talk about the direction 1 minus 1 0 at further talk. Some other equilibrium magnetic states is possible when we apply external magnetic field, external electric field, or elastic strains. In this case, we can get some other equilibrium states. Speaking of practical applications of bismuth ferrite, there are suggestions to use this material as exchange by as an antiferromagnetic layer coupled with a ferromagnetic layer in spin wave structure, and due to these magnetoelectric properties, it's possible to make magnetoresistive memory cells possessing ultra-low energy dissipation and controlled by application of voltage between multiferroic layer. There are also suggestions to use these magnetoelectric properties in logic devices, the so-called magnetoelectric spin orbit logic devices. And because we can, in bismuth ferrite and other multiferroics, we can control magnetic states, it's possible to change magnon or spin wave spectrum using external electric fields, and it's possible to create switchable magnonic devices using these antiferromagnetic materials. As I said, ferroelectric structure is strong in these materials, and there are three types of ferroelectric domain walls. Namely, it's 180, 109, and 71 degrees ferroelectric domain walls. We will consider 180 degrees domain walls because it's the simplest case, and it leads to most interesting magnetic properties because it switches the Zelashinsky vector. I have not much time, but let's say we consider a periodic ferroelectric structure, which was previously considered in a decade ago by Professor Gareyeva and Zvezdin. We tried to reconsider this case using the global optimization method. The global optimization methods allows to find a global minimum of some function. The function we consider is a thermodynamic potential, which was on the previous slide, and it allows us to calculate a spatial distribution of antiferromagnetic vector, the Neal vector, in space for periodic ferroelectric domain configuration. Here I presented a geometry of our problem. We have two ferroelectric domains divided by 180 degree domain wall, and in our problem we suggest that both polarization and anti-distortion vector are rotated in different periodic domains. We also consider periodic boundary conditions and the boundary on this geometry. What we get as a result of our calculations is a spatial dependence of the Neal vector. Here you can see a dependencies of components, spatial components of this Neal vector, and we considered a case when a length of this periodic ferroelectric structure gradually increases. So we start with 72 nanometers, and at the ground state, corresponding to the minimum of the energy of our structure, spin spiral takes place. When we increase the size of our structure, the periodicity of our spin spiral increases, but the total structure doesn't change. But when we achieve some critical value of size of ferroelectric domains, the abrupt change takes place. The inter-domain distribution of the Neal vector changes, and also changes the boundary states at the domain wall, ferroelectric domain wall position, and the internal structure, magnetic, the periodicity of spin spiral decreases, but an additional half of period of this periodic structure adds to the distribution. And when we further increase the length of our structure, we can see other abrupt changes of the structure inside the ferroelectric domains. Such like structure when a half of period added every time we achieve some critical length of our size of our ferroelectric domain size. And our conclusion that, first of all, spin spiral configuration corresponds to the minimum of the energy, and it represents the equilibrium magnetic state of the multiferroic or multiferroic at single crystal state or for film structure deposited on some substrate. The second is the widening of ferroelectric domains leads to a two-stage process, which includes a widening of antiferromagnetic domains, retaining boundary states at the domain wall, domain boundaries, and increase of period of the spin spiral, the so-called widening of period of spin spiral. And at some critical lengths of ferroelectric domains, an abrupt change takes place. Well, I guess I don't have much time. You can ask me some questions.
Thank you very much, Sergej, for an interesting presentation. We have a hand raised and a question from S. Rotha, AtC University. Could you please unmute yourself and ask the question? The participant which has a hand raised with the name S. Rotha from AtC University, could you please unmute yourself and ask your question? Okay, maybe he's gone for a while. I would like to ask for the participants who is not familiar with the field so much, what was the main challenge? Oh, okay.
Am I audible?
Yes, now we can hear you. Yes, please ask your question.
Okay. Can you please tell me how we can measure this spinning site in the domain wall experimentally? Is it possible?
Sergej, you are muted. Sergej, you are muted. Yes, we can hear your question, but Sergej is muted. That's why we cannot hear him yet.
Do you hear me now?
Yes, we can hear you now.
Okay. Repeat. What do you want to? Thank you for the question. What do you want to measure? I didn't understand.
Actually, I want to measure the spinning site, domain spinning site experimentally. Is it possible?
Domains
spinning site.
Well, there are few techniques for measurements. The first technique is piezoelectric force microscopy, which allows to measure ferroelectric domain patterns of films. Second technique is magnetic force microscopy, which works when ferromagnetic layer deposited on top of the antiferromagnetic multiferroic. And the third technique is a novel NV magnetometry measurements, which allow to measure spin distribution, magnetization distribution of films at nanoscale, at the nanoscale.
Okay, thank you very much.